Okay, we're live. Welcome back, everyone. If you're watching live or if you're watching on capture, this is the workshop series for the BUIDL Battle Hackathon with Stacks, co-hosted by DoraHacks. So welcome back. This is workshop 7, titled Building Native Bitcoin Smart Contracts on ICP. I'm joined today by Morritz from Dfinity. Morritz, how's it going?
Going great. What about you?
Good stuff. Yeah, going really well. Just recovering from ETH Denver. So just a quick reminder for the hackathon, there are 11 days left. It's live now. You can go ahead and register. The link to the DoraHacks hackathon page will be in the description. If you have any questions, you can put them in the group chat and we'll ask them to Morritz at the end. If you have any questions after this session, remember there's a Telegram group that you can use for support, the link to which is in the details section of the hackathon right at the top. So go and jump in that. Even if you haven't got questions, just jump in and it's a good way to stay in touch. But without any further ado, I'll hand over to Morritz and I'll put your presentation up there and then the floor is yours.
Thank you. Yeah, as already mentioned, today I'm giving a workshop, this time kind of a hands-on workshop. So on Monday, I talked about the internet computer in general and more specifically about the Bitcoin direct integration and chain key signatures. So in today's workshop, I assume that you were present on Monday. So if you have not been present on Monday, some of the things I'm talking about might be a bit difficult to understand, but I think you could still follow along and then just rewatch the recording from Monday, and then things should click. So, as already mentioned, I'm going to cover today how we are able to build native Bitcoin smart contracts on the internet computer. And even though I cannot cover everything I talked about on Monday, I'm still going to give you a very quick intro in case you were not there. So, quick reminder, the internet computer is a decentralized and permissionless cloud built on blockchain technology. And because the internet computer is a decentralized cloud, you can think of canisters, this is what we call smart contracts, as decentralized servers. And that is because they have access to a number of pretty unique capabilities provided by the Internet Computer Protocol. And the first one I want to talk about here is in the top left corner, called timers. So using timers, you can automatically execute contract logic, either after a specified delay or periodically. So you could, for example, say, execute this function in 10 years, or you could say, execute this function every 5 years, or you could also say, in 10 years, execute this function every 5 minutes. All possible. Usually need some off-chain infrastructure for things like that. So I don't know, some cron job that calls into your contract, but here this is something that the system provides. Next cool feature is the reverse gas model. What does that mean? That simply means that your users are not required to pay for transactions on the internet computer. And how it works is that you, as a developer, when you deploy a contract or a canister, recharge that canister with gas. This is what we, with gas, and on the internet computer, we call gas cycles. So whenever some computation is being carried out by the smart contract or some data is being stored, the cost for that is covered by the cycle balance or gas balance that the canister holds. And that's pretty nice because with that, you don't need to onboard users to browser extension wallets, and you don't have to onboard them on centralized exchanges or something, so they can get their hands on some of your layer 1 currency so that they are able to pay for transactions. No, all of this is abstracted away, which is pretty neat if you want to serve or cater non-Web3 people with your product. Another really cool feature is the fact that canisters can call into Web 2. Usually, if you want to get information from outside of the blockchain, you need to set up some sort of Oracle service, but on the internet computer, this is kind of like built into the protocol, so you can just make an HTTP out call like you would do on Web 2. So you specify the URL you want to call, the type of request that you want to make, maybe a post or a GET HTTP request, headers, and of course also a payload. So very straightforward. And then the smart contract makes this HTTP AUK call, and the information is available in the context of the contract. With this, you could, for example, call, I don't know, some price feed to get the latest Bitcoin price, or you could maybe settle a prediction market about who's going to win the national chess championship or something like that. It's very flexible, so up to you what you are going to use it for. And the next is also provided by the protocol. I simply say web speed here. What it means is that the time it takes for a message on the IC to be finalized is roughly 1 to 2 seconds. And that means that you can build dApps that operate at web speed. So when a user interacts with a dApp that you deployed on the internet computer, for them, it's hardly kind of like distinguishable from any other Web2 application that they interact with. Because when they do a write, so for example, I don't know, they create a profile in your dApp and that is persisted in the canister's memory, then it takes only 1 to 2 seconds until that message is finalized. And that's pretty neat, again, to onboard users, so they don't need to wait like 10 minutes until a transaction is finalized, or in the case of Bitcoin, even 60 minutes. On to the next one, on-chain randomness. So again, something that's provided by the protocol. We have secure and verifiable random numbers available in the context of a canister. This is also something that you usually would need an oracle for, but here not necessary. Then chain key signatures. This is part of kind of like a number of features that we summarize under the term chain fusion. And chain key signatures, in very short, allow canisters to have control over unique ECDSA and Schnorr key pairs, and to also request signatures with the corresponding private keys. And what it enables them is that they are able to natively hold currencies like Bitcoin, Solana, Ethereum, and I think all of the relevant layer 1 assets. And that is because they mostly support either ECDSA or Schnorr signatures. And this is what we are going to use today, actually. And then also canisters can store huge amounts of data, currently 500 gigabytes per canister, and that only costs you $5 per year per gigabyte. And last but not least, you cannot only serve your backend or your business logic from the IC, you can also put your UI or your website in a canister. So canisters can serve web natively into your browser, and it's not necessary for the user to download any extension or something. It just natively serves HTTP into browsers or command line applications, whatever. All right, so because we want to build native Bitcoin smart contracts, of course, we somehow need to be able to read from and write to Bitcoin. And also sign transactions for Bitcoin. So for this, there are 2 key building blocks. And that is that, first of all, we need to be able to verify consensus of the Bitcoin network within the internet computer. And therefore, we have the Bitcoin direct integration. And that provides an API that we will have a look at in a second. And then the other key building block is that when you want to make state-changing operations, so to say, so if you want to submit a transaction to Bitcoin, we need to be able to sign the transaction from within the canister. And this is where chain key ECDSA or chain key Schnorr, you can also call them threshold Schnorr, threshold ECDSA signatures, come in very handy. And then, of course, you also need your canister smart contract to integrate with those 2 APIs. And we will take a look at how this works in a couple of minutes. So quick recap, Bitcoin API, this is covered in more depth in the talk I gave on Monday. So it's essentially an API that allows us to read and write Bitcoin state. And through this API, you have access to 6 different functions. First 2, Bitcoin get UTXOs and Bitcoin get balance, I guess self-explanatory. So you provide an address and you get the information what UTXOs belong to this address or what balance this address has. Then Bitcoin signed transaction, that allows you to submit a signed transaction to the Bitcoin network from within a canister. And then Bitcoin get current fee percentiles. This is handy when you construct your transaction because you want to make sure that it's included. So you want to set an appropriate fee. And then Bitcoin get block headers with this. A canister could, for example, fetch raw transactions with a Merkle proof from an untrusted source and verify that they are indeed part of the Bitcoin blockchain. So this is reading from and writing to, right? 4 methods for basically reading and 1 method, send transactions, for writing. But now, second building block, we need to be able to sign a Bitcoin transaction that we want to submit to the Bitcoin network. And here there are 2 APIs or 2 functions on the ECDSA API. One to get a public key for a canister. A canister actually doesn't only have access to a single public key, but by providing this derivation path, access to many, I would say, unlimited public keys, and therefore also unlimited Bitcoin addresses that it can control. And of course, for the public key, and therefore for the addresses, it is able to sign transactions with ECDSA. And this is what we use this sign with ECDSA function on the right-hand side. And basically exactly the same thing we have for Schnorr. So a method to get a public key and another to sign a transactions. So in the practical part, what are we going to do? Or what is our goal? So we are a Bitcoin whale, and we want to keep our exposure to Bitcoin. But we don't want to hold the Bitcoin on an exchange. So we want to have self-custody. But at the same time, we think very far in the future, and we say maybe someday we will be gone, and we don't really want to bother our relatives or friends with managing our keys that control our Bitcoin in case we disappear. Because maybe they don't understand it and you don't trust any other person to help them with that problem. So you basically, when you decease, you want to have a way that, a secure way that your relatives have access to your Bitcoin without putting them on an exchange directly. And one way you could do this is that you build a deadman switch and an escrow for your Bitcoin. And the idea here is that because canisters on the IC can control Bitcoin and can send transactions to the Bitcoin network, that we basically put our funds in the custody or under escrow of this smart contract. And because we write this ourselves and we are great programmers, of course, we trust that there's no smart contract risk. And because it's a smart contract, we trust that there's no single entity that can just like take our Bitcoin from us. So this seems to be good enough for what we try to achieve. And the idea here is that we check in regularly with the canister to ping it and say, hey, I'm still here, I'm still alive. And in the case we don't check in regularly, or we don't check in within a predefined interval, the Bitcoin that the canister holds are sent to an address that we provide when deploying the canister, and that address is or belongs to one of our relatives and is connected to a centralized exchange. So you could imagine that, I don't know, your wife or husband, they have a Coinbase account, and within that Coinbase account, they have a deposit address for their Bitcoin, and this is the address that you give to this canister to send your Bitcoin to in case you don't check in within the predefined interval. So that is the idea. So let me stop sharing the presentation and let's start with the practical part. Yeah, this looks good. So what we are basing our project off is this tutorial or this piece of documentation on the Internet Computer developer portal. You can reach it by going to docs.internetcomputer.org. That will basically redirect you here. And then you can go to building apps. You scroll down to Chain Fusion, and then Bitcoin, interacting with Bitcoin, and then developing locally. A bit hidden, but you can also use the search functionality up here to find it. And the first things we have to do are to set up a local Bitcoin network. And I already walked through the steps on my machine, so I'm not going to repeat them, but it's pretty straightforward. You basically just download Bitcoin Core, do a bit of configuration, and then run it. And because we already downloaded this and did the necessary preparation, we can now start the Bitcoin daemon, and that will run a local Bitcoin reg test network on our machine. And the second thing we need is that we base this off of an example that lives in our examples repository, and that example is called the basic Bitcoin example, and instructions on how to do that for 2 different languages, Motoko and Rust. Motoko is our domain-specific language, Rust is Rust. I'm going to use Motoko, and I already cloned this. So I'm going to open a new tab here. I'm going to this directory. I renamed the example folder into BUIDL to make it more apparent. Then we go into the Toko subdirectory and then into the basic Bitcoin. And then we are going to open this in Visual Studio Code. And the first thing we are going to do is that we actually deploy this. So to deploy this, we first need to start DFX. And DFX is a command line interface that allows us to spin up a ICP node locally. So it's basically the same thing that we did for Bitcoin, but now we do it for the Internet Computer. And the outcome is that we have one testnet for the Internet Computer running locally, another testnet for Bitcoin running locally, and the Internet Computer testnet is able to talk to the Bitcoin testnet that is running locally. And this is exactly the situation that we have on mainnet. So on mainnet, there is a Bitcoin activated subnet, and that the nodes in that subnet, the physical machines, they run a so-called Bitcoin adapter, and they are able to ingest blocks from the Bitcoin network and then forward them to a special canister and so on and so on. But this is all covered in the talk from Monday. So if you are interested in how exactly this works, I recommend you check it out. So we're going to, first of all, stop DFX in case it's already running, which doesn't seem to be the case. And then we're going to start it. So this spins up this local ICP node and our local ICP testnet. So here we have Bitcoin running locally, and here we have the IC running locally. So let's create a new tab in the same directory, and let us deploy the code, the example code from this basic Bitcoin example locally. And here we can provide an argument to the deployment. So in this case, this is a variant, and the specific, what's the name of that actually? Well, a variant with the specific value of reg test. So this basically tells this Bitcoin example to not talk to the Bitcoin mainnet, to not talk to the Bitcoin testnet, but instead to talk to the reg test that we currently run locally. And that's why we need to provide this deployment argument to tell this example what Bitcoin network we want to interact with. All right. This is now getting built and then deployed locally. And that's basically the first step. So let me go back to VS Code and quickly go over the actual code. So previously I showed you this Bitcoin API. that developers can interact with to access certain information from the Bitcoin network. As you can see, this is basically redefined in here. So we have all the methods that we saw earlier, right? We have get balance, get UTXOs, get current fee percentiles, and also send transaction. The thing that's missing is that the headers, but for this example, we don't need it, so it's not defined. So this is how we, within this example, are making this Bitcoin API available. So that's a canister that's called the management canister. In the future, this is actually going to change, but I think this is out of scope for this workshop today. And yeah, here we are simply able to make the exact same calls that I mentioned earlier to this Bitcoin API. So it's pretty straightforward, I would say. So we call this management canister that exposes the Bitcoin API, and we wrap those calls within another function, because we actually, in this case, we have to pay gas or cycles for the management canister to be able to make those calls. And this is done here with add cycles. This basically adds gas to this call. But anyways, so this is the third part, right? The Bitcoin API to read from and write to the Bitcoin network. And then we have one for ECDSA. And those are the two functions that you would expect. So we are able to get an ECDSA public key, and we are able to sign with ECDSA. So yeah, pretty straightforward, I would say. And then, of course, the same thing for Schnorr. Here again, we have the opportunity to sign with Schnorr and to get a Schnorr public key. And as you can see, they are all encapsulated, or those three APIs are now encapsulated and separated as separate modules to make things a bit more structured and streamlined. And then we also have other modules, like, for example, this pay to public key hash module. And this, as the name already suggests, allows us to create those kind of transactions and then also send them to the Bitcoin network. So in here, there's actually a package. It's called the Bitcoin package or library that is published on a package manager that you can include when you build on top of the Bitcoin API, and that simplifies creating transactions a lot. So I definitely recommend you to use this. And they also depend on this Bitcoin API, because this is needed to set a transaction, for example, or to get the fees. And then also ECDSA, because this is the signature scheme used for the pay to public key hash transaction types. And for pay to taproot, it's basically from a mental model the same thing. But in this case, so you can see up here, this now imports the Schnorr API and not the ECDSA API, because those type of transactions require Schnorr signatures and not ECDSA signatures. But the rest is similar, I would say. Okay, so those are all modules, and they again are imported in our main.mo file. This is basically the entry file of our smart contract. So in Motoko, the public interface of a smart contract is defined within such an actor object. And in here, we have a couple of functions that are publicly callable. For example, this get balance function, get UTXOs function. And this is again just a wrapper around the Bitcoin API, right? So this is made publicly available, and under the hood, this canister makes a so-called inter-canister call to the Bitcoin API to get the balance for the address that has been provided on the correct network, which is this deploy argument that I mentioned earlier. But there are not only, there are two different types of public facing functions. So there are update calls. They look like this. They just have public func as, let's say, a prefix when you define them. And then there should also be query functions. I'm not sure if there's one in here. Does not look like it. I'm still going to explain it because there's a quite a difference between them. You could, for example, write a query in here, and then the call you are making, this doesn't work because query calls are not compatible with inter-canister calls, but in theory, if you would see this query keyword here, that would indicate that the call is basically similar to a contract call on Ethereum. Or is it a contract call? It's basically a read operation, so there are no state changes, so they don't go through consensus, so it only takes roughly 100 to 200 milliseconds until they return. If you call one of the state changing public functions, for example, those update calls like get balance here, they go through consensus, and then it takes 1 to 2 seconds until they are finalized. And this is probably something I should have covered at the beginning. It's kind of like the configuration file for your internet computer project. It's called defects.json. And in here, we define, for example, what canisters we are implementing for this specific project. And in this case, there's only one canister called basic Bitcoin, and we see the entry point is specified here. So this is the main.mo file that we looked at. And we also specify the type, because you can actually write smart contracts on the IC in a number of languages, for example, also in Rust or JavaScript, TypeScript, Python, C, and so on and so on. So in this case, we specify that it's Motoko, which is our domain-specific language. All right, so let's go back to the tutorial, because what we want to do now is we want to actually, at least locally, give our canister Bitcoin. And I'm going to open this thingy here already, and I'm going to explain a bit later what it is about. But for now, let's see in the documentation how we are able to receive Bitcoin for this specific canister. So we go into the directory of our, going to put this over here, in the directory of our local, where our local rec test or Bitcoin rec test resides. Then we run this following command. It's just copy pasted, and here we basically indicate that the address that we are specifying here has minted X amount of blocks. In this case, 1 block. Not minted, mined. And of course, now we need to know what is the address of our canister. And luckily, if we go back into the code and we check the interface that the canister provides, we can see that there are functions to get the different types of addresses for the different types of transactions for this canister. In this case, we are sticking to the pay to public key hash address. So how do we get it? The easiest way of getting it is to head to this website. So whenever you deploy a canister locally, it usually spits out this URL that's also running on localhost, and that is basically a candid UI. Candid is like an interface description language for canisters on the IC, so similar to an ADI for ETH contracts. So we have this nice default graphical interface or user interface that basically shows all the functions that the canister exposes and allows us to call them either with whatever we provide as an argument or with a random argument. So for now, we want to get the public or the address for this canister, the pay to public key hash address for this canister. And this is it. So now we are going back to our local Bitcoin rec test, and we are telling that should not have happened. We are saying mine 1 block to this address. Great. If we go back, we also see a function that allows us to check the balance of an address. So this is our canister's Bitcoin address, or one of the addresses, and let's check the balance now. As you can see, indeed, we now have, I don't know, I think it's 50 Bitcoin or something, probably, for the first block that was ever mined on this local rec test. That's great, but unfortunately, because of the Coinbase rule, we cannot spend it yet unless there are 100 more blocks mined. So this is actually also explained in the docs. When you go down a little bit, this is what we just did. So we mined one block and then check the balance of our canister that it actually received the block reward for this block. And now we are going to just create 100 blocks to this random address to be able to spend the Bitcoin, or we let this random address mine 100 blocks to be able to spend the 50 Bitcoin or 500 or how much it is that is owned by the canister. And that looks like this. So those are all the transaction hashes from those blocks. Oh yeah, it's 50 BTC. Okay, and now we are able to actually spend those Bitcoin. And for this, we are going to actually just take this random address that's provided here. We're going back. Actually, let's first check the balance of this random address. Should be 0. Okay. And now we can send, let's say, 100 Satoshis to this random address. And then ideally should work. Takes a little time. Yeah, it took 8 seconds. That's because it's not, there are inter-canister calls involved. So it's not, I'm not only interacting with one canister, I'm calling one canister, that canister calls another canister, and there's some latency involved there. So it seems like this worked. So let's check again if we now have 100 Satoshis. No, we don't. Okay, perfect. Let's see if we missed something. Let's check the address and the balance of our canister. If this is at least less now, also not the case. Oh, then let's maybe just try this again. Or maybe let me try a different address. So let's check this one. Should be empty. I think I have to mine a block first. Yeah, that makes sense. Should also be written here. Yeah, there still remains. Yeah, I should read the docs. It helps. There still remains one additional step, which is to mine a block, so that the transaction you just sent becomes part of the blockchain. That makes a lot of sense. Let's do that. So now we mined a new block, and within this block, this transaction that we just then should be included. So now if we go back, and which one was it? Was this N thingy? I think it was, yeah. Now this should have 100 sets. Still not. It looks like it processed. Let's see again. Okay. Let's check our canister's address if at least this one is lower now. Also not. But this should work. Let's go back to the docs and see if we are missing something critical. So we sent from our pay-to-public key hash address to this address. Maybe we need to send more Satoshis. I don't know if there's a kind of like minimum amount. Okay, let's mine another block. Or maybe 2 blocks. Hopefully I'll be able to stay within time. Okay, this at least worked now. Yeah, maybe I didn't send enough. Not sure what exactly the issue was. But now we should be able to, to see that the balance of this address increased by the 100K sets that we sent over. Okay, that it worked. All right, let's continue with actually changing what we currently have in this example, because this doesn't really do anything except that I can generate an address, I can send Bitcoin to that address, and I can transfer Bitcoin out of that address, all through the public interface that the canister provides. But we want to get to this deadman switch kind of situation, right? So what we start with is so-called init args. So those are arguments that we provide to the canister when we install it. And what we want to have here is, this is actually almost helpful. We want to have a network, and then we want to have an inactivity timeout. That's a net, it's a natural number. Network is the different types of networks that are available. So regtest, mainnet, and testnet. And then we also want to have a Bitcoin address. And this is just text. So, oops, don't know what that was. So yeah, inactivity timeout basically says, how long do I have to be inactive in seconds? I should add that probably, seconds. How long do I have to be inactive? How many seconds do I have to be inactive until the canister triggers and sends the Bitcoin that it holds to this predefined address? And the predefined address is provided as the BTC address down here. All right, that looks good. Now let's go back to our main.m. Also right now, this only takes an argument called network, but we want to provide init args, right? So we go types init args. And what we also want to do is we want to turn this into a shared actor class so that we can, call that equals deployer, so that we can get the deployer of this canister. And this helps in, this helps in figuring out what principal actually deployed this canister, so what address deployed this canister, because the deployer of the canister should have some privileged access to functionality on the canister. And now this is changing to init args.network, and then we also have stable that deadline. No, not deadline. What was it called? Inactivity timeout seconds. Inactivity timeout seconds. Init args. Oh, that was camel case. Not Rust, Motoko. And then we have the Bitcoin address. Okay, so far so good. Next, we are going to set up one of those timers that I mentioned. So first, we're going to add 2 variables, is alive, which is a Boolean and initially false. And then we are going to specify a variable where we can hold the ID of our timer. So timers, when you set them up, those cron jobs that I mentioned at the beginning, they always have an ID, and that ID allows you to cancel them. And we are going to create this caller, and then this is called start. It's asynchronous and returns nothing. And now we can set up a recurring timer. There's a extension for VS Code that allows us to, that comes with some macros, so to say. So makes it a bit easier. So this is called timer ID. And then I want this to run every inactivity timeout seconds. And then this should be async actually. And return nothing. And here I need to import timer from the base library. And then in here, I'm just going to copy paste this because I have everything. I'm very short on time now. Going to actually copy pasting all of it just to make sure that I didn't make any error, and then walk you through what's happening. So this is a timer. The timer is triggered every inactivity timeout second. So whatever we provide to the canister when deploying it. And then when the timer is triggered, this function is executed. And this function does at first a simple print. It allows me to debug it a little bit better, saying I'm now executing the timer. And then it checks, is the deployer still alive? So did the deployer within this inactivity timeout ping the canister and say, hey, I'm alive? If that's the case, then it resets the is alive variable to false. And then I would need to ping it again so that the next time this executes, it doesn't go into the else clause down here. If I am not alive, so I did not trigger or ping the canister within the inactivity timeout, this happens. And what this is basically that it gets the address of the canister and stores it here, the Bitcoin address. Then it gets the balance of that address, so the balance that the canister currently holds, and stores it in here in this variable. And then it sends a Bitcoin transaction, a pay-to-public key hash transaction on the Bitcoin network to the Bitcoin address that we provided. So in this case, to this Coinbase kind of like at the deposit address from, I don't know, your spouse or whoever. So this is where I'm sending it to, and the amount that I sent is the balance that the canister currently holds minus a fee of 2,000, just a random fixed fee to make things simpler. And then, because I mean in this case I don't need this Deadman switch anymore, I'm also going to cancel the timer so that it doesn't like continue to run just for environmental reasons. Not really necessary, but I mean, why not? Okay, but how do we tell the canister now that we are still alive and that it should not send the Bitcoin to the Bitcoin address of my spouse on Coinbase? For this, I'm going to create another function. By the way, those callers that I add here, they do what you think they do. They tell what they within the context of the function, they allow me to determine who called that function. And that is becoming a bit more important in a couple of minutes. So again, this is an asynchronous function that doesn't take any arguments, that doesn't return anything. And the only thing that it does is it sets this variable is alive that we specified, or that we declared up here, to true. So this is my, hey, I'm still alive, kind of like call. And now we are going to specify this is not public, this is just internal. I can still define functions in here that are not publicly callable or callable from the outside. In this case, I'm going to specify a guard, and the guard takes one argument, and that is a principal. This is what we call addresses or identities on the internet computer. And in here, I basically make an assertion. And what I assert is that the deployer equals to the caller, or that the principal, or that the canister is the caller. Caller, yeah, this, oops, looks right. And I now am going to add this guard to all the functions where it's necessary. And of course, I don't want to let anyone to start my admin switch, but myself, right? So what I'm going to do here is I'm going to guard this function. So if someone calls this function that does not have the identity or the key or the address that belongs to the deployer of this canister, then the execution basically stops here because this assertion is not valid anymore. Of course, same thing for this keep alive, right? If anyone could be able to call it, then that wouldn't really be helpful, right? Because then my spouse would never get their Bitcoin because some random person could always say, he's still alive. So I just want to be the one that's allowed to call this. And then I also want to add this to the send methods that are in here. So let's search them, because I don't want to allow other people to just randomly send the Bitcoin that I add. Yeah, now I also have to add this caller thing. We're going to do that in a second. Let's do it one by one. Send, because otherwise anyone could just send or transfer out the Bitcoin that I gave to the canister, and that wouldn't be ideal, right? I want to be the one that's allowed to do this. So let's do this again. Maybe I'm going to copy this. Insert it here, and also public shared. I also need to share it, of course I do. Public shared, and public shared. So now only the deployer of the canister is able to transfer funds out of the canister, and that's what we want. That's good. All right, let's test this now. Let's redeploy this canister locally, and let's also restart our local Bitcoin reg test, because right now the canister already holds some funds, and I want to have a clean state. So I'm going to stop this. Then I'm going to remove the data directory. I'm going to recreate it. This is what you have to do, and then I'm going to start it again. What's the command? Not this, not this. This looks good. All right, now we should have an empty, fresh, clean Bitcoin reg test locally, and I'm going to do the same thing for our DFX or Internet Computer Network locally. And yeah, once that has started, I should be able to deploy the canister again. So this time I'm not going to provide this argument because it would be wrong, right? We changed the init arguments. We have this type now, so we need to provide a record with 3 entries: network, inactivity timeout, and seconds, and Bitcoin address. So if I would send this deploy argument, the deployment would fail. The cool thing is I don't need to specify it because there's actually kind of like a wizard that allows me to specify them interactively, and that should pop up in a second if everything went well. Building, installing. Great. So now it asks me, hey, what do you want to have for the inactivity timeout? And I want to have 45 seconds. And I want to choose again our reg test network that we have set up locally. And for the Bitcoin address, I want to use this random address that now corresponds to the Coinbase deposit address from my spouse. Do I want to initialize the canister with those arguments? Yes, sir. Send it. Great. That worked. Now, what do we have to do? We have to go back to our Cadet UI and check again what is actually our address, because if you redeploy the canister, very likely this address changes. You have to reload. It's kind of like a small detail I won't be able to explain, but if you see this, just reload the page, hard refresh, and you're good. So it should be 0 now. Yes, because there's no block, right? And certainly we didn't mine it. So we are going to run this command again that mines 1 block to our canister's address. And again, we have to mine, or we can first check, did this work? Not yet. Takes a little while. Now it works, great, but problem is we cannot spend them because of this Coinbase maturity rule. So again, we are going to mine 100 blocks to this random address. And now we should be able to spend them. So remember how we added those guards, right? So on this UI here, I'm not authenticated, right? So I should be able to call this keep alive function without it erroring out. As you can see, indeed, I cannot call it. I should also not be able to call one of the transfer methods here because they also all have this guard. Perfect. So now only I, as the deployer, can call those guarded functions. And I'm going to do this, or I have to do this, with the identity that deployed the canister. So with the identity that is associated with my DFX, so with the CLI2 that I'm using. And here, first of all, also let's check the balance of this exchange, right, to make sure that there's no crazy magic going on. This should be 0. Perfect. So our canister has 50 Bitcoin, and my spouse's Coinbase deposit address doesn't hold any Bitcoin. So let's actually start the statement switch. We have this beautiful start function here, this one, that we can call, and then the timers start executing, right? Right now, nothing happens. There's no timer. If I call start, I'm going to trigger those timers, those recurring timers. So every 45 seconds, according to our init arc, this function down here is executed. So let's do it. DFX is actually easy. You call, you execute, or you type DFX canister call, and then what's the name? Basic Bitcoin, and the function I'm going to call is the start function. So, oh yeah, there's a typo. It's not basic Bitcoin, it's basic Bitcoin. Beautiful. And next, of course, I quickly, because I only have 45 seconds, want to call basic Bitcoin keep alive. Whew. Okay, so now I have the opportunity to. So what happens now is that this with this keep alive that I called down here, I actually changed this initially set to false variable to true. So when the timer executes, it doesn't end up in this branch here. It ends up in this branch, so it does nothing because it knows I'm still alive. It just sets this back to false, so I have to, within 45 seconds, call it again. And I can actually see this by checking the logs of the canister. So this debug print here, this debug print here is available when I call DFX canister call logs. Those are previous logs from the triggered traps where the assertion, the guard basically kicked in. But now we can see, a couple of seconds ago, the timer was executed. And but nothing should have happened, right? Let me quickly, before 45 seconds, execute again. Check the balances here. So this balance is still 0. This is the deposit address from my spouse. So we went into the right branch. But now I'm not doing anything. And I'm basically, this variable is now set to false. So when this executes again, I'm not in this branch, I'm in this branch now. And this branch should transfer all the Bitcoin that the canister escrows for me to the Coinbase deposit address that we set up when we deployed the canister. So let's check this again. And as you can see, now the timer executed again, roughly 45 seconds after the first one, which is good because this is what we wanted. And now there are a couple of more logs, one for telling me that a transaction has been built, what fee this transaction kind of like set out to give to miners, and then that the transaction was actually sent. Okay, that worked, which is great. So now let's check the balance again. Still 0 because we need to mine a block. Let's do that first. So we again mine 1 block so that this transaction is actually mined and included to this random address. And then after a little while, after the local ICP network picked up on the actual transaction for the Bitcoin adapter, I should be able to see the balance. Great. So now my spouse, I'm not alive anymore, which is very sad, but at least my spouse has the Bitcoin in Coinbase and can now cash out and buy a nice car, all the jewelry they always wanted, a house, maybe a pet dog, something like that. Yeah, takeaways, it works. And let's also check the balance of the canister. And that is, as expected, 0. So if we wanted to change the arguments of this, the init arguments of this canister, so basically those things here. So we say, yeah, I want a different timeout. 45 seconds is not enough. Maybe give me 3 months. Every 3 months I check in. And we just redeploy the canister. And if there are no code changes, what you need to do, maybe a bit of side note, you run dfx deploy basic Bitcoin, and then you add upgrade unchanged. And that should allow me to, yeah, basically redeploy the canister, even though there were no changes, because usually dfx kind of like checks, okay, there were no changes, so I'm not going to redeploy this canister, and that can be a bit hindering. So now let's take, I don't know, 1000 seconds, still reg test, and this random address. And boom, now we have new settings for our deadman switch. All right. Add time, beautiful. 2 minutes left. Okay. There were 2 questions.
Yeah. Hey, Morritz. Great presentation.
Thank
you.
So
the questions we've got from the audience are, number 1, I found a project called Dfinity, an EVM Bitcoin layer 2 on ICP. Is that relevant to the hackathon?
Unfortunately not, because I mean, it's a really cool project and very nice for EVM developers to get started quickly. But at the moment, to my knowledge, they do not support this kind of like low-level raw access that we provide to the Bitcoin network through building canisters directly on the internet computer. So you, for example, you cannot create a transaction on Dfinity EVM and a Bitcoin transaction and then submit that to the Bitcoin network. That does not work to my knowledge. So you would need to build natively on the internet computer. But here, even though Solidity is not one of the languages, you can use Motoko, which is what I just showed. You can use Rust, and you can also use JavaScript or TypeScript. So those 3 languages are all supported, and they also all support the Bitcoin API and also threshold signing for Schnorr and for ECTSA.
Awesome. Okay. Yeah, but good find, hacker. Definitely check out Dfinity, just not for this hackathon. And then the second question is, why is the Bitcoin get balance not query? Sounds like a read operation.
Yeah, that's also a very good question. So it is a read operation, that is correct, but because the functionality is not provided by this canister that we just built, but by another canister, what happens is an inter canister call. I can quickly show this here in the Bitcoin API. So you said get balance. Yeah, get balance. So here, as you can see, we call the management canister. So we make an inter-canister call. And unless you use a special type of call that is not set up here, you need to do this through update calls. Long story short. So it is a read, but yeah, in this case, it is not, because it's an inter-canister call. And also from if you do inter-canister calls, they cannot be queries. They always have to be update calls. And they always have to go through consensus. So they will always take at least 1 to 2 seconds. A great question. Well, yeah, I don't know how to say this in English, but shows that you watched with great attention.
Sure. Yeah, great. And just a reminder to everyone, if you're watching this on catch up, thanks for tuning in, and you can ask any questions in the Telegram group, where there is a link in the hackathon page, the BUIDL Battle hackathon page on DoraHacks. So jump into that group and ask any questions if you have any after watching this workshop. And this actually brings us to the end of the workshop series with Stacks and all the partners for this hackathon. So thanks to Morritz and thanks to everyone else for taking the time to help educate the community, and I'm really looking forward to seeing what people build.
Yeah, thank you for having me. It was a pleasure. And yeah, have a great evening, day, morning, whatever it is.
Good stuff. You too. Thanks, everyone.
Bye-bye.